Okay, welcome to the video tutorial on OH as a leaving group. A lot of you, you'll see problems where OH might be a leaving group. You might think OH might be a leaving group. And put simply, you should memorize this in red. Hydroxide, OH minus, or any other kind of equivalent base, methoxide, ethoxide, T-butoxide, those are never leaving groups in E2 or SN2 reactions. Okay, so this is important. And it's only hydroxide. So for example, why would this be? So OH, let's say we have, so why can't we do this? So why doesn't this work? So you would identify hydroxide as a leaving group, methoxide would come in and kick out hydroxide. That looks like, so mechanistically, that looks just like an SN2 reaction, right? Primary alcohol, strong base, good nucleophile, so why doesn't this work? And the reason is, well, there's two reasons. Kinetically, the carbon-hydrogen bond is pretty strong. All right, so that gives you a very high activation energy. The carbon hydroxide bond, it takes a lot of energy to break a carbon oxygen bond. The second reason is, so two, we're going to see acid-base chemistry. The most likely thing for the methoxide to do is in fact take that proton, and you'll establish an acid-base equilibrium. So really, any nucleophile strong enough to come in and displace hydroxide is going to be basic enough to pull that proton off. That obviously doesn't apply if you want to have methanol or methoxide or ethoxide as a leaving group, only number one. Number one is enough to not have this reaction happen. So, put bluntly, simply, hydroxide, methoxide will never be a leaving group in an E2 or SN2 reaction. So, better leaving groups are weaker bases. Right? If we think about what leaving groups we know of. So chloride, bromide, iodide, those are all weak bases. Also, sulfonate esters are good leaving groups. That's basically the conjugate base of sulfuric acid or a sulfonic acid. These, in fact, are better leaving groups So chloride is a worse leaving group than bromide, which is a worse leaving group than iodide, which is a worse leaving group than a sulfonate. But these are basically it in terms of the leaving groups that we're going to look at. Okay, so again, weak bases are good leaving groups. Hydroxide, methoxide are never good leaving groups. Never a leaving group in SN2, SN1, or E2, E1. So what happens though if you let's say I ask you to do this transformation. How might you do this? How might we turn that alcohol into a methoxide? There's actually a few different ways. There's a lot of different ways. The first thing you might do, and this is important, probably the best way, use the alcohol as a nucleophile. Okay, so in this one, we use a base to make the alkoxide, and then use methyl iodide as an electrophile. There you go. That gets your product. Use that oxygen as a nucleophile rather than try to kick that oxygen out. And the base you might use for this would be, the best base, I'll just tell you one, is sodium hydride. This is effectively H-, and you make hydrogen gas. All right, that's one way to do this. And it's a good way. It's probably the best way. All right, I'm going to erase this, so hit pause and write this down and think about it if you want. The second way is to convert that OH to a leaving group. And there's two different ways to do this. So we can do, there are two reactions you're going to need to know. They're in the textbook. If you treat an alcohol with phosphorus tribromide or PCl3 or PI3, that converts the alcohol to a bromide. You don't need to know the mechanism of this reaction, but you should know the reaction. An alcohol plus phosphorus tribromide will give you an alkyl bromide, and then you can displace that with methoxide. Okay, that's straightforward. You can also use thionyl chloride. How about I write that correctly? SOCl2, and that will convert the OH to a chloride. Treat that alkyl chloride with methoxide, and there you have the product. The second way is a little more complicated. So write this down. You need to know these two reactions. All right. So know that if you have an alcohol treated with PBr3 or SOCl2, you'll get the halide, the corresponding halide. The second way, you'll recall I've talked about sulfonate esters. So as a leaving group, that's a good leaving group. And what you can do is turn this oxygen into that oxygen. All right. And the way we do this is to treat this alcohol with the corresponding sulfonyl chloride. And now the sulfur is quite electrophilic. The oxygen displaces the Cl. You make HCl. And you get the sulfonate ester. And now when we treat that sulfonate ester with methoxide, we kick out the sulfonate ester, methoxide comes in as a nucleophile, and we get our product. So you need to be able to do this as well. At least recognize when a sulfonate ester could be made. We have two different names. So when R is CH3, this is called, can be abbreviated as OMS, or is called a mesylate. When R is equal to the toluene group, so this is, would be that. This is called the tosylate, or OTS. You'll see this in the book. And again, just recognize that mesylates, tosylates, any sulfonates are really good leaving groups. They're excellent in this regard.